Welcome to Chapter 9, where we're going to be diving into wide area networking. Today we'll explore WANs, routing, security, and troubleshooting. So let's get started. What exactly is a WAN? I want you to think of it like a long distance relationship above the networking world. It covers significant distances and it requires high data throughput to keep things running smoothly. But here's the thing, not all businesses need the same type of WAN. It's kind of like ordering pizza. Your choice depends on your traffic load, your budget, how far you need to reach, and what technology is actually available in your area. You can't order deep dish pizza from a place that only makes thin crust, right? So the difference between WANs and LANs, LANs are like your home network. They connect individual devices in a small area. WANs are the highway system that connects entire cities. Here's what makes them different. LANs connect nodes while WANs connect entire networks across wide geographical areas. They can differ at the physical and data link layers, but they speak the same language at the network layer and above. And here's a big one. Most companies own their LANs, but you own your home Wi-Fi router. But WANs, those are usually leased from carriers, like renting a car for a cross-country road trip. So let's break down your WAN connection options. First up, broadband versus DIA. Broadband is like sharing a highway. Cables and bandwidths are shared between multiple customers. It's asymmetrical, meaning downloads are faster than uploads. Perfect for binge watching Netflix, not so perfect for uploading your company's entire database. Then there's DIA, which stands for Dedicated Internet Access. This is your own private highway. The bandwidth is all yours. It's symmetrical, so downloads and uploads are about the same speed. It's like having a lane on the freeway that only you can use. Expensive? Absolutely. Worth it for mission critical applications? Absolutely. Let's talk about DSL and cable broadband. DSL, or digital subscriber line, runs over good old telephone lines like the PSTN or the public switched telephone network. Your DSL modem has ports for both phone and data devices, so you can talk to grandma while downloading all those videos. Cable broadband runs on the same coax cables that bring you your 500 cable channels of nothing to watch. It was standardized through DOCSIS, which stands for Data over Cable Service Interface Specifications, which sounds like a robot's autobiography, honestly. Cable typically offers asymmetric speeds, so again, it's great for streaming, not so great for uploading. Now, here's where things get fancy when we get into fiber optics. ISPs are increasingly offering FTTC, which is fiber to the curb, or FTTH, which is fiber to the home. It's like upgrading from a dirt road to a superhighway. Lease lines provide dedicated bandwidth on fiber optic connections with three major advantages. Dedicated bandwidth, that's all yours. Symmetrical bandwidth, so uploads and downloads are equally fast. And an SLA-backed guarantee, which is service level agreement. It's basically a promise from your provider that if things break, they'll actually fix them. It's like having a warranty that actually works. So if we look at this diagram, you can see why each location needs its own leased line to connect to the ISP. It's like each branch office having its own private tunnel to headquarters. Your storefront in the city, your warehouse in the suburbs, and your other storefronts all need their own dedicated connections. No sharing, no congestion, just pure dedicated connectivity. It's expensive, but when you absolutely positively need to get that data there overnight, this is how you do it. So now we enter MPLS, which is multi-protocol label switching. And don't let the name scare you. Think of it as a package delivery system where every package gets a special label that tells routers exactly where to go without having to open the package and read the address every single time. It lets routers function more like switches, which saves time and reduces latency. It's like having an express lane at the post office, but for your data. MPLS allows multiple types of layer 3 protocols to travel over various layer 2 protocols, which is the universal translator of networking. This diagram shows how MPLS creates one big happy network family. Your headquarters with its lease line, your warehouse connected via DSL, and all your storefronts with fiber broadband. They all connect through MPLS domain over the ISP's network. The beauty is that MPLS provides cohesive WAN management for multiple connection types. It's like having one universal remote that handles your TV, your cable, your sound system, and that weird lamp that only works when you press the right button connection. When it comes to cloud connectivity, reliability is everything. You've got three main options. You've got the internet, which is the cheapest but least reliable, kind of like hitchhiking to work. You've got a direct connection, which is you get a dedicated line straight to your cloud provider's data center. And large providers maintain multiple points of presence around the world, like having multiple entrances to a theme park. And finally, VPN, which is virtual private network, which creates a secure tunnel over the internet, kind of like having a secret passage for public mail. SD-WAN is the cool new kid on the block, stands for Software Defined Wide Area Network, and it uses centralized control to manage network functions. It's like having a really smart traffic controller for your entire WAN. The benefits are impressive. It's transport agnostic, meaning it works with any connection type. It offers application-aware routing, or sometimes abbreviated to AAR. The network actually knows whether you're on a Zoom call or downloading updates and prioritizes accordingly. You get active load balancing with automatic failover. If one path goes down, Trafficly instantly reroutes. Plus, intent-based management, zero-touch provisioning, and reduced costs. Basically, the Swiss Army knife of WAN technology. This diagram shows the magic of SD-WAN in action. Your home office, your branch office, and various connections. There's a 5G wireless WAN, broadband, and MPLS, and they all connect through the SD-WAN managed connections. The SD-WAN controller intelligently directs traffic through the optimal path for that specific traffic at that specific time. Notice that X over the MPLS domain, maybe it's down, but SD-WAN automatically reroutes traffic through 5G or broadband. It's like having a GPS that not only knows about traffic jams, but automatically takes you around them. Wireless WANs are designed for high throughput, long distance digital data exchange. So let's pivot to cellular networks. They started as analog phone services. Remember when phones were actually for just calling people? Today, cell networks deliver both data and voice. 4G, or fourth generation, gave us an all IP network with speeds from 100 megs to 1 gig. Then 5G arrived and said, here we go. Fifth generation requires minimum speeds of 1 gig and maxes out at 20 gigs download and 10 gigs upload. That's fast enough to download an entire movie before you finish making popcorn. So this slide's about satellite internet. A handful of companies offer high bandwidth internet access via GEO satellite links, which is geosynchronous Earth orbit, satellites that stay in one spot relative to Earth. Satellite services are typically asymmetrical, and bandwidth is shared among many subscribers. Throughputs vary and are controlled by the service provider. The big advantage, you can get internet in the middle of nowhere. The disadvantage is latency. Your data has to travel 22,000 miles down to Earth, up to space, back and forth. That's like asking someone a question, waiting 2 seconds for them to answer every single time. So here's how satellite communication works. You've got your satellite in orbit above Earth with a transponder that receives and transmits signals. The uplink goes from your dish to the satellite, and the downlink comes back down to another location on Earth. Meanwhile, Earth is rotating beneath the satellite. It's kind of like an elegant dance in space, beaming your emails and videos across continents. Just remember, when you're video conferencing via satellite, that awkward pause isn't social anxiety, it's just physics. Okay, time to talk about routers briefly, which is really the unsung heroes of networking. A router joins two or more networks and passes packets from one to another. Think of it like a postal worker who actually knows where everything goes. Routers can connect dissimilar networks like LANs to WANs. They interpret layer 3 to layer 4 addressing, which is IP addresses and port numbers, and they determine the best path for data to travel from point A to point B. And if that path is blocked, they find another route, like a GPS that actually works in tunnels. Routers can also perform optional functions that make them even more valuable. They filter broadcast transmissions because not everyone needs to hear everything. They prevent certain types of traffic from getting to a network, kind of like a bouncer at a club. They support simultaneous local and remote connectivity. They provide high fault tolerance through redundant components. They monitor network traffic and report statistics, which and lastly, they diagnose connectivity problems and trigger alarms. So they're kind of like the hypochondriacs, but in a good way. So categorizing routers, we've got core routers, also called interior routers. They are the direct data between networks within the same autonomous system, or AS, which is a group of networks operated by the same organization. They're like internal mail delivery within a large company. Edge routers or border routers connect your autonomous system to the outside world. They're the gatekeepers. Exterior routers refer to any router outside your organization's AS. They're like the routers of the internet backbone. These are the routers you don't control but definitely depend on, like the highway system you drive on but you don't maintain. So this diagram illustrates the router hierarchy. On the left, we have one autonomous system with core routers handling internal traffic and an edge router connecting to the outside. In the middle, we have exterior routers from ISP1 and ISP2. These live on the internet backbone. And then on the right, another autonomous system with its own core routers and edge router. Data flows from core to edge to exterior to edge to core. It's like a relay race, but everyone has to pass the baton correctly or your email never arrives. A routing table is a database that holds information about where hosts are located and the most efficient way to reach them. Routers rely on routing tables to identify which router is the next hop to reach a particular destination host. Think of it as a GPS map, but for networks. Routing tables contain IP addresses and network masks that identify which network a host or another router belongs to. Without routing tables, routers would be like mail carriers without addresses, just throwing letters in random mailboxes and hoping for the best. Now, routing paths are determined in two ways. We have static routing, is when a network administrator manually configures the routing table to direct messages along specific paths. It's like writing turn-by-turn directions on paper. It's reliable but inflexible. A common example is a static route between a small business and its ISP. Dynamic routing is where routers automatically calculate the best path between networks and maintain this information in their routing tables. The router can detect problems with failed or congested routes and reroute messages through different paths, like having a GPS that automatically avoids traffic jams. Much smarter, but much more complex. The route utility lets you view a host's routing table. It's like peeking at the router's map. You can also use it to add or delete static routes. The command varies by operating system. On Linux or Unix, you just type route in the command line. On Windows, you type route print in a command prompt. On Cisco's iOS, you enter show IP route at the CLI using privileged exec mode, which sounds very official and important because it is. It's like asking directions, but from a computer. Routing metrics are properties routers use to determine the best path to a destination. Think of them as the criteria you use to choose a route to work. Do you care most about the distance, the time, tolls, or avoiding certain intersections? Common routing metrics include hop count, which is how many routers you must pass through, theoretical bandwidth versus actual throughput, which is the speed limit versus how fast traffic actually moves, delay or latency, which is how long the journey takes, and load, which is how much traffic or processing burden exists on the path. More routing metrics to consider. We've got maximum transmission unit, or MTU. That is the largest IP packet size allowable without fragmentation. Think of it as the size limit for packages on an airplane. Routing cost is a value assigned to a particular route, like toll fees. Reliability is how dependable the path is, and network topology is the overall structure of the network. Routers consider all these factors to make intelligent decisions. It's like choosing between taking the highway that's faster but costs tolls versus the scenic route that's slower but free. The router weighs all options, picks the best one based on current conditions. Routing protocols are how routers communicate with each other to determine best paths. They're constantly chatting, sharing information about network conditions. Routers rate the reliability and the priority of routing protocols based on 3 criteria. First, we have administrative distance, or AD, which is a number indicating the protocol's reliability. The lower is better, like golf scores. You have convergence time, which is how fast the network recognizes a best path when something changes or fails. It's like how quickly everyone agrees on a new meeting time when the conference room becomes unavailable. And then we have overhead, which is the burden placed on the network to support the protocol. Some protocols are chatty and consume lots of bandwidth, just talking about the network. So let's talk about gateway protocols briefly. We've got exterior gateway protocols, which are used by edge and exterior routers to distribute data outside autonomous systems. They're for communicating between organizations. You have interior gateway protocols, which are used by core and edge routers within autonomous systems, therefore internal communication. IGPs are often grouped by the algorithms they use. Distance vector protocols calculate paths based on distance to the destination, like choosing the shortest route. Link state protocols enable routers to communicate beyond just their neighbors, and they have a broader view. Hybrid protocols combine characteristics of both, the best of both worlds, or the worst, depending on your perspective. So let's talk history and current technology. Routing Information Protocol is the oldest routing protocol and is now considered obsolete. It's the flip phone of routing protocols. Open shortest path first is an IGP and link state protocol with impressive characteristics. It supports large networks, uses complex algorithms, has shared data among routers, offers low overhead and fast convergence, and provides stability. OSPF is like the reliable sedan of routing protocols. It's not flashy, but it gets the job done well, and it rarely breaks down. Intermediate system to intermediate system is an IGP and link state protocol that uses a best path algorithm similar to OSPF. However, it's designed for use on core routers only, unlike OSPF, which works on both core and border routers. It's the specialist to OSPF's generalist. Then there's Enhanced Interior Gateway Routing Protocol. It's a distance vector protocol with some link state features, earning it the nickname Hybrid Protocol. EIGRP offers fast convergence and low network overhead, and it's easier to configure and less CPU intensive than OSPF. It's like OSPF's more laid-back cousin who still gets good grades but doesn't stress as much. Border Gateway Patrol is the only current EGP, and it's known as the protocol of the internet, so no pressure. It spans multiple autonomous systems, connecting the entire internet together. BGP has special characteristics. It's a path vector routing protocol, which is like distance vector but tracks the entire path. It's efficient, it's customizable, and it's extremely powerful. But BGP is also the most complex routing protocol we've discussed. Learning BGP is like learning to fly a commercial airline. You need serious training, but once you master it, you can really go anywhere. Redundancy keeps networks running when things fail, and things will fail eventually. Active redundancy means all redundant resources are active simultaneously and work is distributed among them. It's like having multiple cashiers open at a store. Everyone's working all the time. Active passive redundancy means only one or a few resources are active with backups on standby. It's like having backup cashiers on break, ready to jump in if needed. First hop redundancy protocol provides a virtual IP address as the default gateway. This includes VRRP, HSRP, and GLBP, three protocols that accomplish similar goals with different approaches. They're like having multiple spare tires, ensuring that you're never stranded. Internet connectivity brings amazing opportunities and significant risks. As they say, with great connectivity comes great responsibility. Connecting to the internet can ruin organizations or careers if security isn't taken seriously. WAN security is absolutely critical for any network connected to the internet. Think of it as locking your doors in a neighborhood where millions of potential burglars constantly walk by. Some are just window shopping, but others are actively looking for unlocked doors. You may want to be the house with the security system, not the one with the door hanging open. ACLs, or access control lists, allow routers to decline forwarding certain packets based on their content. An ACL acts like a filter or bouncer, instructing the router to permit or deny traffic based on network layer protocol, transport layer protocol, source IP address, and destination IP address, and TCP or UDP port. On Cisco routers, you use the access list command to assign statements. For example, to deny ICMP traffic from any IP address to any other IP address, you type in access-list 101 deny ICMP any. It's like telling the bouncer, nobody gets to ping anyone, no exceptions. Proxy servers act as intermediaries between external and interior networks, screening all incoming and outgoing traffic. They're like bouncers who check everyone's ID, both people trying to get in and people trying to leave. Proxy servers manage security at the application layer of the OSI model. They provide relatively low-grade security compared to other security devices. So they're more like a gentle reminder to behave than a strict enforcer. But they can help prevent attacks on internal network resources like web servers and web clients. Think of a proxy server as the first line of defense, but not the only line of defense. So here's a diagram that shows a proxy server positioned between the internet and your internal network, and it's behind a router with a firewall. Workstations connect through a switch to the proxy server, which then handles all communication with the internet. The proxy server examines every request going out and every response coming in. It's like having a personal assistant who reads all your mail first, decides what's safe to open. The proxy can cache frequently accessed content, filter malicious sites, and also monitor usage. It's not perfect security, but it's better than letting everything through unchecked. Now we move to firewalls. Firewall is a specialized device or software that selectively filters or blocks traffic between networks. Most commonly, firewalls sit between private networks and public networks, like the internet. These are network-based firewalls. You also see firewall features integrated into routers, switches, and other network devices. It's become a pretty standard feature, kind of like power windows in cars. Host-based firewalls only protect the computer they're installed on, like Windows Firewall or Mac OS Firewall. They're your personal bodyguard, while network firewalls protect everyone in the building. So this diagram shows the classic firewall placement right between the internet and your private network. Firewall acts as a gatekeeper, examining all traffic that tries to cross the boundary. Workstations inside the private network can access the internet through the firewall, but the firewall controls what gets in and what gets out. It's kind of like airport security. You have to go through the checkpoint when you're arriving or when you're departing. The firewall inspects every packet, checking against checking against its rules to decide whether to allow or to block it. The simplest form of a firewall is a packet, which is a filtering firewall. It examines the header of every packet it receives and refers to its firewall rules to determine whether to block incoming traffic or exiting the LAN. This is inbound traffic filtering. Think of it like, once again, like a bouncer checking IDs at the door. Firewalls often ship with default configurations designed to block the most common security threats. It's like having a new phone with some security settings already turned on. It's good, but you'll want to customize it for specific needs. Out-of-the-box security is better than no security, but customized security is the best. Some common criteria that packet filtering firewalls use to accept or deny traffic include source and destination IP addresses, who's serving and who's receiving, source and destination ports, which is which applications are involved, flags set in the TCP header, which are special instructions in the packet, transmissions using UDP or ICMP protocols, which are different types of network communication, a packet's status as the first packet in a new data stream or a subsequent packet, which is, are you starting a conversation or are you continuing a conversation? And a packet status as inbound to or outbound from the private network. Are you coming or are you going? The firewall considers all of these factors before deciding whether to allow the packet through. The next generation firewall takes things further by monitoring and limiting traffic of specific applications and adapting to specific users, user groups, applications, or devices. It's like having a bouncer who not only checks IDs, but also recognizes regulars, knows who's on the VIP list, and can make judgment calls based on behavior. UTM, which is Unified Threat Management, combines multiple layers of security appliances and technologies into a single safety net. A UTM solution provides a full spread of security services managed from a single point of control. It's like having home security, a fire alarm, carbon monoxide detector, and flood sensors all managed from one app. It's comprehensive, it's convenient, and it's also very powerful. Optional firewall functions to consider include encryption, which is scrambling data so only authorized parties can read it, user authentication, which is verifying who people are before granting access, centralized management, which is controlling multiple firewalls from one location, easy rule establishment, because life's too short to struggle with complicated configurations, logging and auditing capabilities, keeping records of everything for security and compliance, protecting your internal LAN's net address identity from the outside world, which is keeping your internal network structure private, monitoring packets according to existing traffic streams, which is understanding context, not just individual packets. And lastly, application layer filtering, which is examining the actual content and application data, not just the headers. Firewall rules function similar to ACL rules, but with more granular control. ACLs function on a single interface at a time, like having a security guard at one door. Firewall rules provide broader control to secure traffic as it enters, exits, and traverses the network, like having a comprehensive security system throughout the building. Rules can check for information such as port, protocol, IP address, or CIDR range. Think of firewall rules as kind of a sophisticated questionnaire, asking what port are you using, what protocol, what's your source address, where are you going? And then based on your answers, the firewall decides whether you're allowed through or not. This flowchart shows how firewall rules are processed. When a message arrives, the firewall checks the rule first. Does the rule fit? Does the first rule fit? If it does it deny traffic? If so, it drops the message. If it allows the traffic, it lets it through. If the first rule doesn't fit, it checks the next rule. The firewall continues down the list until it finds a matching rule or it reaches the end. If it reaches the last rule and it still doesn't have a match, the default action applies, which is usually deny. Rules are checked in priority order, so rule placement matters. kind of like a bouncer's checklist. If you don't match any of the allowed criteria and you're not specifically banned, you're not getting in by default. When troubleshooting firewalls, remember that the most common cause of firewall failure is misconfiguration, which is human error and not technical failure. The configuration must strike a delicate balance, not so strict that it prevents authorized users from transmitting and receiving necessary data, but not so lenient that you unnecessarily risk security breaches. It's like setting up parental controls. Too strict, nobody can watch anything. Too loose, and you're not protecting anyone. Sometimes you need to create exceptions to the rules, which is referred to as punching a hole in the firewall. Just remember, every hole you punch is a potential security risk. So document everything and only punch holes when absolutely necessary. Cloud platforms embed security technologies within their services to protect against security challenges unique to the cloud. Most cloud security tools offer three key functions: granularity, which is fine-grained control over who can access what; awareness, which is visibility into what's happening in your cloud environment; and default configuration, which is starting with reasonable security settings out of the box. Cloud security works according to the shared responsibility model. The cloud provider is partially responsible for your cloud security, and you're responsible for the rest. It's like living in an apartment building. The landlord secures the building and the common areas, but you're responsible for locking your own door and not leaving valuables visible through the window. Now, when you lose internet connectivity, troubleshooting helps determine where the problem is and who's responsible for fixing it. Is it your equipment, your ISP, or is it something in between? Common issues to look for on your own equipment include interference. Is there physical or electromagnetic disruption? DNS issues. Is your computer cannot translate website names into IP addresses? Router misconfiguration and roaming misconfigurations, which means something's wrong settings-wise. And interface errors, which is a physical connection problem. Before you're calling your ISP and spending an hour on hold, check these things first. It's like checking if your TV is plugged in before calling tech support. Save yourself some time and some potential embarrassment. Several commands provide insight into device and interface performance, vulnerabilities, and misconfigurations. The show config command lets you see the device's running config file with show running config, or sh_run for short. It's like reading a device's mind, seeing exactly how it's configured right away. The show interface command gives you an overview of all the device's interfaces with show interface, or shint. This shows you the status of every connection point on the device, which are up, which are down, which are having problems, kind of like checking all your doors and windows to see which ones are open, closed, or broken. This screenshot shows a router's interface information in a packet tracer. Notice the detailed information. The interface is connected to two VLANs. Hardware and IP addresses are listed. MTU and bandwidth specifications are shown, and there's information about packets, errors, and collisions, and more. Reading this output is like getting a complete health report for the interface. You can see everything that's happening. The key is understanding what you're looking at. Seeing 0 input errors, 0 output errors is good. Seeing thousands of errors, that's bad. Learn to read these statistics and you'll be able to diagnose problems much faster. On a Cisco router, the show IP route command lists the router's routing table information, essentially showing you the router's map of the network. Common routing issues include missing route, which is the router doesn't know how to reach a destination, kind of like having a GPS that doesn't know about a new street that's been recently built. Routing loop, which is packets that get caught going in circles between routers, like being stuck in a roundabout that you can't exit. And then asymmetric routing, which is packets take different paths going out versus coming back in. This can cause problems with firewalls and security devices that expect to see both directions of a conversation. The screenshot shows a router's routing table with multiple entries. You can see codes explaining what different letters mean: C for connected, S for static, R for RIP, and so on. Each entry shows a destination network, how to reach it, and through which interface. Reading a routing table is like reading a complex maps with multiple routes to various destinations. The router consults this table for every packet it receives to determine where to send it next. If you see a destination missing from this table, You found your problem. The router literally doesn't know how to get there. That's a wrap for Chapter 9. So let's recap what we've covered. We compared WAN connectivity technologies from broadband and DIA to fiber, MPLS, and SD-WAN. We explained how routers managed inter-network communications using routing tables, protocols, and metrics to find the best paths. We described ways to secure WAN connections using ACLs, proxy servers, firewalls, and cloud security technologies. And we learned to troubleshoot common connection problems by checking interfaces, routing tables, and configurations. Remember, WANs connect us across vast distances. Routers are the intelligent traffic controllers. Security is absolutely critical, and troubleshooting is a systematic process. Thanks for watching Chapter 9. I will see you all for Chapter 10.